Assalamu alaikum everyone. This is Sohaib Ahmed from GSCRL Lab. Today we are here for the second lecture of World Space Week. The topic of today's lecture is CubeSats. The next big thing is really small. This lecture will be delivered by Mr. Usman Imran. He is the research assistant in SSTRL Lab. He did his master's degree in integrated technology from South Korea. And he did his bachelor's in mechatronics engineering from UT Peshawar. Currently, he's involved in SSTRL Lab and looking after attitude control of iCube and group. And he has been working as a research assistant in Human Robotics Lab, South Korea. Mr. Usman, thank you so much for joining us today.
Thank you,
Now
Sohaib.
I would like, thank you very much. Mr. Usman, you can go live now.
Okay. So, Sohaib, can you see my screen?
Yes, we can see the screen.
Okay. Thank you, Sohaib, for the introduction. And Assalamu alaikum, all the participants. I welcome you all to today's session. So today I will be discussing about the Cube satellites. The next big thing is really small. So basically the Cube satellites, they are really small satellites in terms of size, but if we see them in terms of their applications, they have some really big impact and applications, as we will see in the coming slides. So I begin by introducing the Small Satellite Technology and Research Lab. So this lab comes under the umbrella of NCGSA, National Center of GIS and Space Applications. So some of the major purposes of this lab, the number one is that it is dealing with the CubeSat training equipment. So it would be developing the kits for educational purposes and give it to different universities for education. Similarly, it would be conducting workshops, lectures, and demonstrations. And the third responsibility of this lab is that it would be developing a 3-unit cube satellite. So it would be less than around 5 kg, and it would consist of different subsystems. And the last one is that different universities and colleges would be participating in the development of iCubeN. So this is a brief introduction about Small Satellite Technology and Research Lab. Okay, so moving on, the scope for today's session is to give you some basics of Cube Satellite and the technology that is involved behind the development of those small satellites. And similarly, what could be the applications of these Cube satellites. And the target audience is that anyone who has some basic knowledge of science, and students from grade 6 to 12, similarly undergraduate students. And the expected outcomes is that to give you know-how about satellites, and the major thing is to develop the interest for space, satellites, and their applications. So this would be the outline for today's session. It is divided in 4 subsections. The first one would be background, history, and intro. The second one, subsystems that would be there. Similarly, what could be the applications of these small satellites? And in the end, we will see some example missions, and we will see how the Cube satellites are launched. So in every section, I had included some videos to give you more informative and interesting views. So the first one would be dealing in the background section. We would see why we need to explore the space and what is the need for the satellites. Similarly, what is CubeSat would be defined, and the brief history and the standards and classifications for the Cube satellites would be discussed. And in the end, there would be a video which would be summarizing all these introduction section. And in the subsystems, we will see the components that the cube satellite is made up of. It would consist of structure, solar panel, power system. There would be an onboard computer. Antennas would be there for communication with the ground station. And similarly, there would be the videos that how all these subsystems are assembled. And in the application section, there would be camera. And similarly, what could the spectral imager be used for? And the intersatellite communication, I would discuss about these things. And in the example missions, these missions would be discussed, followed by how CubeSats are launched in the space. So let's begin with the first section, that is background, history, and introduction. Okay, so the first basic question is that why we need to explore the space, that why we should go to space, what is the need? So the number one and the most important is that it can help save the life on the Earth. So as we know that there are many asteroids in the atmosphere, and some of them could be really dangerous for our Earth. And according to statistics, around 26,000 near-Earth objects, which are asteroids, are there, and out of them, 2,000 are considered as extremely dangerous. So the asteroids, anything which is larger than 20 meters, they can cause significant damage to our Earth. So the number one reason could be that if we have some mechanism, we could detect these asteroids, so we can do something to shift their orbit or save the Earth. And similarly, one of the other reasons could be the medical advancement. So like the technologies which we develop by keeping space in mind. So later on, they are really helpful for the mankind. So one of these examples could be the radiation techniques that are used in the medical treatment of cancer. So these are all the spin-offs of the space technology. Similarly, one of the other reasons could be the possibility of life beyond Earth. So it is possible that there are some resources because of which the life there is possible. Similarly, we can have precious metals and elements there, and if we can bring them to the Earth, they could be really helpful for our mankind. And similarly, the other reason could be strategic needs, and the other thing is curiosity. Most of all, human mind is always curious about new things and new technologies. So these are some of the reasons that why we should be exploring space, why we need to go there. Okay, so coming to the next slide, we have why do we need satellites? So as I explained that why we should go to space. So there should be some mechanism or some machinery or some devices that are continuously monitoring our atmosphere so that we can get the data and information we require. So for that purpose, we build satellites. So the satellites, basically they orbit our planet and they can perform different functions and applications. So one of them could be that if they have some camera on board, they can take the images of Earth. Similarly, they can assess the space environment, content of different gases, and the weather prediction that is also made based on those sensor informations. And the one other thing, GPS, as we all have this in our mobile systems also. So these GPS, it has been made possible with the help of these satellites. So we can get the location with the help of these satellites. Similarly, one of the other reason is that it could help in the tracking of ships and planes. So how it helps in the ships and plane tracking, we will see this in the coming slides also. And also you can see in this image here. So when a ship is, let's say, operating in a remote sea, so that it is not able to communicate with its central facility. So what it does is that it has AIS system, which communicates with the satellite, and that satellite sends back information to the central ground station or control room. So these are the things because of which we need satellites. And similarly, in terms of communication, we see that we have TV channels. So these things are also being made possible with the help of these satellites. And coming towards spin-offs, spin-off means that when we develop some technology keeping space in mind, but later on that is helpful for our mankind on Earth. So some of examples are space blankets, which have thermal insulators, and they are really helpful in winter. The firefighting equipment, similarly CMOS imaging camera, which initially took the images of Earth, but nowadays we have the camera in every mobile phone we use. So these are the reasons we need to have satellites so that we can assess our atmosphere. So these are some of the pictures, GPS, atmosphere. This is showing the ship tracking, and this one is demonstrating about aeroplane tracking. So we will see these in the coming slides also. Okay, so moving on to the next slide. So what is basically a CubeSat? So we have seen that a cube satellite, basically it is a 1-unit satellite. So this is the minimum one unit, and it is kind of standard. So its dimensions are 10 by 10 by 10 centimeter, and its mass is around 1.3 kilogram. So it is this much small satellite. And if we want to make multiple units or some bigger satellite, we can combine these units to form 2U, 3U, 6U, up to 12U. So we can make multiple units out of this 1-unit satellite in case if we need more applications or more payloads. So the applications, they depend on the payload which is implemented on that satellite, and it could be multiple. It could be the camera which is taking images of Earth. It could be the gravity measurement meter which is measuring the gravity of different places. So all of these are the possibilities there. Okay, so the next thing is the CubeSat history. So the first CubeSat, as you can see, it was launched in 2003, but the standard reference design, it was proposed in 1999 by California Polytechnic State University. So after the 4 years of the first reference design, the first CubeSat was launched. And the first Cube satellite by NASA, that was launched in 2006. And coming to Pakistan, the iCube-1, which was the first Cube satellite of Pakistan, so that was launched in 2013. And if we talk about the interplanetary missions, so this Marco satellite, which is basically operating and orbiting in the Mars. So this was launched in 2018. And currently the Pakistan at Institute of Space Technology, we are developing another Cube satellite. So it is expected to be launched around 2024. So this is basically the CubeSat history, and mostly until 2013, the CubeSats have been used for educational and research purpose. But in the current era, in the past few years, the shift has been more toward the commercial aspects, that how they could be used for commercial purposes, like providing internet in the remote areas using these small satellites. Okay, moving on, we have CubeSat's history in Pakistan. So these are the images. This is the image of CubeSat iCube-1, which was launched in 2013. And this is also the images from the clean room. And the iCube-1 was basically a 1-unit, which I showed you on the previous slide, that the minimum could be 1 unit. And its mass was around 1.2 kilogram. So it was launched from Russia using Dnepr launch vehicle. And so that was the first one. And currently this iCube-N, which is started in 2020. So it is in the development phase. Okay, so moving on to the standard, as I was telling you that the CubeSats are developed using some sort of standard. So this standard, which was first proposed in 1999. So as you can see, this one is from 2009. So over the time, it has some modifications, but basically what this standard tells us is that how much should be the dimensions, length, and widths, should there be some deployment switches, and similarly, in short, these are the guidelines which developers have to keep in mind when they are developing a cube satellite. So the next thing is CubeSat standard deployer. So when we have built some cube satellite, the next thing is that we want to launch it in the space. So we use these deployers for that purpose. So as you can see, there is some spring mechanism inside these deployers. So when we insert the cube satellite into these deployers and these lids are closed, and then these deployers are placed on the launch vehicle. And when the launch vehicle reaches the desired orbit or altitude at which it is to launch that cube satellite, so these lids open, and due to spring mechanism, the cube satellite is launched into the atmosphere in space. So these are also kind of standard. So meaning whenever an organization or institute is building a cube satellite, it keeps in mind these dimensions so that their cube satellite could fit in these deployers. Okay, so coming toward the classifications, the CubeSat can be classified into these 4 classes. They could be either pico satellite, nano, micro, or small or medium satellite. So the first iQube-1, which was the first cube satellite of Pakistan, that comes in the range of this pico satellite. And currently we are building a 3U, and its mass is around 4 to 5 kg. So that is a nano satellite. And if a satellite is in between 10 to 100 kilogram, that is termed as micro satellite. And from 100 to 1000 kg, the satellite is classified as small or medium satellite. Okay, so here is a video about the brief introduction. So let's proceed to this video.
उस्मान, आपकी वीडियो में साउंड है?
जी सर,
वीडियो में साउंड आ नहीं रहा हमारे पास।
साउंड नहीं आ रहा। साउंड तो
जहाँ से आपने स्क्रीन शेयरिंग की है ना, जहाँ से आपने स्क्रीन शेयर किया वहीं पे वहीं एक ऑप्शन होगी वहाँ पे शेयर डिवाइस साउंड।
ओके,
उसको इनेबल कीजिएगा।
शेयर साउंड, ओके।
What is a CubeSat?
अभी आ रहा है साउंड?
जी आ रहा है, अब ठीक है, चलाएं इसको।
What is a CubeSat? CubeSats are a class of nanosatellite with a standardized size of 10 cubic centimeters. They are launched into space using rocket-powered launch vehicles, or can be deployed from the International Space Station. Applications include Earth observation, weather monitoring, communications, and more. A CubeSat can go from concept development to deployment in less than 8 months. By comparison, it takes over 5 years to design and launch a large satellite. CubeSats generally orbit the Earth at an altitude between 400 and 700 kilometers and travel at a speed of around 8 kilometers per second. That means they orbit the Earth every 90 minutes. An affordable and accessible way to study the benefits of this technology is through CubeSat prototypes. A CubeSat prototype is modeled after space-ready CubeSats and features the same size specifications. Instead of space, they are launched into the lower layers of Earth's atmosphere, the troposphere and stratosphere, which extend up to 50 kilometers. CubeSat prototypes do not require the same strict qualifications as space-ready CubeSats for attributes such as vibration, radiation, temperature, and shock. They instead provide a perfect opportunity for you to craft your own space adventure.
Okay, so that was the end of the first section, which briefly told about the introduction, history, and background. So in this section, we would be discussing about CubeSat subsystems. So these slide is showing basically the overall summary of the CubeSatellite subsystems. So as you can see on the bottom, there is an antenna which would be used for communication with the ground station. Similarly, we have these solar panels here, which would be generating electrical power from the sunlight. Then we have this EPS, electrical power system. So basically the solar panels would also be charging these batteries so that when there is not sunlight, these batteries are able to operate the CubeSatellite. Similarly, there are some electronic boards. This one is for communication. It acts as a transceiver, which would be communicating with the ground station. And when we send some signal from Earth to this CubeSatellite, this device would be helping in assessing those signals. Similarly, we have an onboard computer. So basically, this is the main heart of the CubeSatellite. It would be controlling all of the main functions. And it would also be responsible for controlling and sending different signals to the Earth. And then we have this attitude determination system. So this is used for basically controlling position and orientation of the CubeSatellite. And in the payload section, we can have multiple sensors. We can have camera for taking images of Earth. We can have some sensors for measuring the weather of atmosphere. So these are some of the CubeSat subsystems, which I would also be discussing in brief detail in the next slides. Okay, so moving on, the first one we have is a structure. So the structure for these CubeSatellites, they have to be of a space-grade material. So usually they are made from aluminum 6061 or 7075. And as you can see in this exploded view, that the structure, it is portable and modular. So you can easily screw off the structure and you can easily assemble these structure. And in most of the cases, the structure is ionized so that it can prevent the harsh environment of the space. And it is quite lightweight, meaning that it is less than 400 grams, and it is approximately 300, 350, depending on different components available. So this weight is only of the structure. So when we add other different components in the structure, so overall it goes to 4 to 5 kg, depending on a CubeSatellite unit. So the next thing in the CubeSatellite subsystem is solar panels. So these are some of the images of the solar panels. So as you can see that here in this case, it is deployed, and in this case, it is compact on the body. So these solar panels, they are usually made up of gallium arsenide triple junction solar cells, and it can range from 1 unit up to 12 unit. And usually 1 unit has a mass of around 50 grams. So the solar panel for 1 unit would be around 50 grams, and 2 unit 100 grams, 3 unit 150 grams. And this 1 unit, it is able to produce around 2.3 watts of power. And when there are multiple units of the satellite, so we can get the multiple power by multiplying it to the corresponding unit. The next subsystem is electrical power system. So it basically consists of these battery cells and this electronic board, which helps regulates different voltages. So what it does is that it stores and distributes power. So with the help of solar panel, the energy is stored into these batteries. And then we have regulators, which maintains the appropriate voltage when delivering this power forward to the subsystems. And they can be, usually they are between 3.3 volt and 5.5 volt. But in some cases, for some sensors, we may require 12 volt, but most of the cases, 3 and 5 volts are enough. And these batteries, they are made from lithium iron phosphate. Usually we have lithium ion batteries in our mobile devices and all kind of devices, but these kind of batteries, they are designed using and keeping the space environment in mind. And electrical power system has battery pack and battery unit. Similarly, it has conditioning unit and power distribution unit. So it consists of all this electronics. These cells are used for storing the power, and these different electronic boards, they are used for regulating the voltages and maintaining different powers across the electrical power system. Okay, so the next component is onboard computer. As I told you that this is most of the important components in the cube satellites. So basically it controls all the other subsystems, and it is also responsible for sending the signals back to the Earth. And similarly, when we send signals from Earth to the cube satellite, the onboard computer has to process that signal also. And it consists of microprocessor and memory. Similarly, it has interfaces with other subsystems. And it has role in the attitude control, telecommunication, and whenever there is some failure, so the OBC has to detect, onboard computer has to detect that failure and try to recover that if possible. So these are images of some of the commercial onboard computer available. So these are from Innovative Solution and Nano Avionics. So the next section is about attitude determination control system. So this ADS, it is used for maintaining the position and orientation of the cube satellite. As you can see, there are a number of sensors on board this system. So these sensors could be gyroscope, gyrometer, which can tell us about the position of XYZ axis. Similarly, sun sensor, star tracker, magnetometer, and then we have temperature sensors for measuring temperature of different systems. So all these sensors, they help to determine the position and orientation of satellite in the atmosphere. And then there are actuators with the help of which we can control the position and orientation of this satellite. So these actuators, basically, they have some kind of motor inside it, and they could be of reaction wheel kind, momentum wheel type. Similarly, they could be based upon the magnetic principle, magnetotorgers, or permanent magnets. So this one here is also the image of reaction wheel. So with the help of these actuators, we can control the position and orientation of the satellites. So as you are seeing in this animation, that when a satellite is launched, usually it is tumbling. So what we want is that we want it to stabilize. So with the help of this ADS-CS system, we can stabilize the satellite. So how do we do that? We have sensors which measures the position and orientation of the satellite. And then we have those reaction wheels, which consist of electric motors. So with the help of those, we stabilize this satellite so that it is not tumbling like this. Okay, so the next thing is CubeSat communication. So this is an electronic board which is responsible for receiving the signals from Earth and also sending the signals from Cube satellite to the Earth. So whenever the onboard computer commands this system to send a signal, so basically this radio frequency device, it is sending the signals to the Earth and also receiving from the Earth. So there are different bands, so VHF, UHF. So VHF, basically it operates from 30 megahertz to 300 megahertz. Similarly, UHF, it operates in the range of 300 megahertz up to 1000 or 1 gigahertz. So this is basically the function of this transceiver unit. And these are images of some of the commercial units which are available to buy online. And then we have antenna system, which is responsible for receiving that signal. So in antennas, we can have this UHF over VHF antenna. So again, it operates in 30 to 300 VHF. And then we have this S-patch band antenna. So this antenna, it has slightly higher frequency than the other one. So it operates in the range of 2 to 4 gigahertz. And then we have global navigational satellite patch antenna. So this is also from Innovative Space Solutions. All these are the commercial products which are available. Then there is a ground station. So ground station basically acts as a control room. So whenever we receive signal, we can operate it with the help of this receiving system. So basically in the ground station, we have some sort of antenna on the roof. It could be of this S-band operating in 2 to 4 gigahertz range, or this UHF or VHF, which is less than 1 gigahertz. So we have these kind of antennas, and then we have this receiving device, which is basically connected to these antennas. And then we have a computer here, and there are different softwares with the help of which we can send and receive the commands to the Cube satellite, which is in the space. So this is the function of the ground station. So this video, the subsystems which I have told you all, the electric power system, structure, similarly the other systems, payloads. So how all these are integrated and into a one subsystem. So this video will help you get a better understanding of that. So let's move to the video. So this was the brief overview of how the Cube satellite goes from structure and combining different subsystems to the final product. So moving on to the next section, we have the CubeSat applications. So I will be discussing about what kind of payloads we can have on the Cube satellite and what would be the applications of those payloads. So basically, payload is any device which we can implement on the Cube satellite and that performs a particular function. It could be a camera, a spectral imager, or it could be a propulsion unit. So the camera, if we have a camera on board, we can use it for taking the images of the Earth. So in case of spectral imager, it basically distributes the image into the number of electromagnetic spectrum, and which is really helpful for detecting objects and different gases or other things in the atmosphere. Similarly, the propulsion unit is helpful when we want to maneuver the cube satellite from one orbit to the another, or maybe at the end of the mission, if we want to deorbit our satellite, and then we can use this propulsion unit and maneuver our cube satellite. As you can see in this image also that some sort of chemical is releasing from these nozzles. So basically, this is the result of propulsion unit that we can maneuver our cube satellite. And similarly, then we can have automatic identification system on the cube satellite. So these are the sensors which could be utilized. So the first one is camera. It could come in variety of sizes and ranges. So as you see, this is with a small lens. Then we have the camera with the bigger lens. So of course, these, if we want to take the higher resolution images of the Earth, we opt to go for these kind of cameras. So all these cameras, they are basically commercial products, and we can tailor them according to the requirement on our cube satellites. Okay, so the next one is Spectral Imager. So if you look at this image, you see it is looking like a camera, but how it is different from a camera, that basically it utilizes the electromagnetic spectrum. So when, if you look at this picture also, so this is the case of multispectral, where an image is divided into discrete subsets. And in this case, there are a number of bands. So it is a continuous band of electromagnetic spectrum. So which is really helpful when we are detecting objects or separating different kinds of gases, because all of these things have different electromagnetic spectrum, and we can detect it with the help of this device. So if we consider the human eye, so human eye basically have these three wavelengths: long wavelength, medium wavelength, short wavelength, or RGB we can say. But whereas this hyperspectral image, it has continuous wavelength and more than 20 bands, as opposed to the human eye, which has only 3. So which is really helpful for detecting objects and different other purposes. So this image here is showing that how it is mounted on a cube satellite. So let's have a look at some of the applications of these spectral imagers. So the first one is that it can help us to detect the objects. Similarly, it could help to identify the materials. It could be useful in agriculture, because with the help of this device, we can distinguish between the crops, field. Similarly, we can distinguish, as you can see here, that this one has more water, less fertilized, healthy crop. And the eye care. So this is also the product of the spin-off. So when this camera spectral imager was developed, keeping space in mind, but later on it was helpful in the eye care. How it was helpful in eye care? Because as I told you that it has a continuous spectrum. So it is helpful in detecting the eye diagnostic. So it could help in detecting those eye-related diseases. Similarly, it could be helpful in food processing, mineralogy. We can find minerals with the help of this, or it could be used for surveillance, astronomy, and environment. How it could be useful for environment, that we can measure different amount of gases in the atmosphere. And similarly, we can make the weather predictions based on that. Similarly, it could be useful to monitor the ozone layer of the Earth. And in the next slide, we will also see some of the applications where the Cube satellite is monitoring the ozone layers. So these are some of the applications that the spectral imager could perform. Okay, so the next one is propulsion system. So these are some of the images of commercial propulsion units. And this Cube satellite is demonstrating that how the propulsion, it is maneuvering through the orbit. So what it does is that we can modify the orbit of a cube satellite with the help of the propulsion system. and we can use it for attitude control. Similarly, at the end of mission, when we want to deorbit our satellite with the help of this propulsion unit, we can do that. And similarly, for collision avoidance, it can be used too. And it could be made up of chemical based, or it could also be the electrical based. So in electrical based, we have further types, like it could be working on the principle of charged particles, or in the base of some heating system in case of electrothermal. And similarly, in electromagnetic system, we would have some kind of magnetic field, and it would be working on the principle of that. And alternative options could be that it has some nuclear-based fuel. So this propulsion unit, it is basically helpful when we want to maneuver our cube satellite and shift our orbit. The next application is automatic identification system. So this is the electronic circuitry for that and some sensors. So how it works is that, let's say that some ships are operating in the remote sea where it is not able to communicate with its ground station or control room. So what it does is that it can send signal to these cube satellites, which also have this AIS system. And then these satellites could send this data back to the Earth. So this is how it works and operates. Okay, so the next one is inter-satellite communication. So this is really helpful when there are a number of cube satellites which are working together to perform a certain mission. So if we look at this image, so you can see there is a constellation of these cube satellites. So there are 3 cube satellites, and this one is focusing on detecting these forests and ices. Similarly, this one is focusing on this area. So it is really helpful when we have a constellation of cube satellites, so we can cover a large area. And similarly, it could be helpful in the case of this ship tracking, which I told earlier. So the satellite which is more nearer to that can receive the signal and transmit it to the ground station on Earth. So the inter-satellite communication could be useful in many science missions. It could be helpful in gravity mapping. So there are a number of cube satellites. So we could have gravity mapping at different points. Similarly, finding water resources, near Earth environment, etc. So these are some of the benefits of constellation of cube satellites. Okay, so this section deals with some example missions and how the cube satellites are launched into the orbit. So the first one is the Marco mission. So it is basically a first interplanetary mission in which the cube satellites are orbiting the Mars. So it consists of 2 cube satellites, Marco A and Marco B, and it has some deployable radio antennas. So basically this works like that: when the Mars InSight lander lands on the Mars, so these cube satellites are orbiting the Mars. So the InSight lander sends data to these cube satellites, and then these cube satellites send data to the Earth. So there is also a video which is explaining the working of this Marco cube satellite. So let's proceed to that video.
Communicating between Mars and Earth requires a complicated choreography, with everything in the right place at the right time. Sometimes hours can pass before information is relayed from one planet to the other. That's why when NASA's Mars InSight lander launches this year, the rocket will carry 2 tiny satellites on a technology test of their own. Meet Mars Cube 1, Marco, NASA's first CubeSat mission to deep space. These briefcase-sized satellites will travel separately from the InSight lander while they test out new miniaturized technologies. And if they make it to Mars, they could relay information back to Earth about InSight's descent and touchdown, and do it in mere minutes. Although this fast communication isn't crucial to the success of the InSight lander, this CubeSat test could change the way future spacecraft phone home.
So as you see in this video that the Mars InSight lander lands on the surface of Mars. and the cube satellites which are above the atmosphere of Mars. So they can communicate. So the InSight lander communicates with the cube satellites, and cube satellites communicates with the Earth. So these are the applications and advantages of the cube satellites. So the next one is GOMX-1. So this cube satellite was launched in November 21, 2013. So it is basically a software-defined radio, research-based. So it was helpful in tracking the commercial flights. So it was a two-cube satellite which had two payloads. So the one was imaging system, meaning camera, which could take the images of the Earth, and the other one was ADS-B payload. So this is basically automatic dependent system broadcasting. So it helps to monitor the commercial air flights, and in case if there is some mishap, the satellites could help or try to communicate with these commercial aircrafts. Then the next one is this SIMBA mission. So this is a 3U cube satellite which can help in the climate change. It basically has solar irradiance sensors and environment. So it could help to identify and monitor different climate parameters and could predict the weather could predict the weather based on those parameters. So this was the function of this small cube satellite, which was named as SIMBA. So basically it was dealing with climate parameters, and it was predicting the weather based on those parameters. Okay, so the next one is the Picasso cube satellite. As you can see in this animation, this is orbiting in the space. So Picasso stands for Pico satellite for atmospheric and space science observations. So this is Pico satellite because it could be falling in the range of the Pico satellite. And as it is a 3U cube satellite, which is dealing with the climate change, and it also has a hyperspectral imager, which I explained in the application sections. So what this sensor is doing on this Picasso satellite, it is measuring the ozone distribution in stratosphere. So it is helping the monitoring of ozone distribution, and then it can predict or sends that data back to the Earth. Similarly, it is measuring the temperature profile of the mesosphere, and it is helpful in the remote sensing. Okay, so the next one is this Hera mission. So it is expected to be launched in 2023. So as in the introductory slides, I discussed about the asteroids and how they could impact our Earth, and they could be dangerous for the Earth. So this mission basically deals with that. So it is a planetary defense mission. So in this mission, there would be two cube satellites, which are named as Juventus and Milani. And the asteroids which it is dealing with is Dimorphos and Didymos. So how it is working, there is a video also. I will go to that. And so basically it would help monitor those asteroids, and in case if there is some mishap event, it could deflect the orbit of those missions so that it would not fall into the Earth or cause damage to the Earth. So how it would be able to monitor and damage the Earth? So there is an animation video for that. So I hope you find it informative and interesting. So let's proceed to that video.
The incredible adventures of the Hera mission. Asteroid on collision course with Earth. Imagine the headlines. It may sound like science fiction, but to date, we've discovered more than 20,000 asteroids whose orbits bring them dangerously close to Earth. It's a hazard the dinosaurs were powerless to stop. With all the advanced science and technology in our hands, could we do better? Planetary defense requires planetary cooperation. Meet the Hera mission, led by the European Space Agency, set to rendezvous with a binary asteroid system in 2026. Didymos is orbited by a smaller asteroid, Dimorphos. This pair poses us no risk, but our experiments with them will be key to keeping Earth safe. Dimorphos is a small asteroid, yet a rock of its size could devastate a small country or large metropolitan area. Studying asteroids like this from Earth is challenging. As a matter of fact, today we still know very little about their physical properties. The only way to capture their secrets is to go and visit, so we need Hera to get up close and personal. When Hera reaches it, Dimorphos will already have been impacted by NASA's Double Asteroid Redirection Test, or DART for short. This cosmic shove is expected to slightly shift the orbit of the asteroid moon. Hera will examine the crater left by DART, the composition of Dimorphos, map its surface temperature, and probe its internal structure, similarly to an X-ray. Meanwhile, Hera will deploy two briefcase-sized CubeSats called Juventus and Milani. Packed with high-tech equipment such as a low-frequency radar, a mineral mapper, dust analyzer, and a gravimeter, these mini-satellites will get an even closer look before attempting to land. Altogether, the DART impact and Hera's data will let us understand whether this technique can be used in the future to deflect an asteroid on a collision course with Earth, like an astronomical game of billiards. In addition to Hera's main planetary defense quest, the mission will gather invaluable bonus science. New understanding of collision physics and crater creation could revolutionize our understanding about how the solar system was formed. Hera will even test new techniques for autonomous deep space navigation and guidance, while working in the asteroid's extremely low gravity. This will help pave the way for future interplanetary missions. Not bad for a space probe the size of an office desk. Hera, defending Earth, one asteroid at a time.
So as you see in this video that how a small desk-sized satellite and then the two cube satellites further emerges from them, and they are monitoring those two asteroids, and in case if there is some mishap, and they can collect data for the further future informations. So the next CubeSat is the RainCube. So it was launched on July 13, 2018. It was also dealing with the weather and climate related things. So basically it would measure different parameters, and it has a radar-like structure on its top. And it would measure different atmospheric parameters and predict weather based on that. So this cube satellite was deorbited on December 24, 2020, and it was burned in the Earth's atmosphere. So this was basically a 6U CubeSat radar, which had this dish-like antenna payload. And the next one in the list is Iqbal, which is the national cube satellite of Pakistan. So this is currently in development at SSTRL lab, and it is expected to be launched around to 2024. So the missions that this cube satellite would be performing would consist of Earth observation. It would be having an camera on board for taking the images of Earth. Similarly, it would be able to communicate with the ground station, which is at IST. And similarly, a spectral imager would also be there on board, which would be able to measure different layers of gases in the atmosphere and send those data back to the Earth. And there is a possibility that a propulsion unit would be also implemented on this iCubeN. And all these things, they would be in-house development that would be developed at Institute of Space Technology in the SSTRL lab. And the multiple universities, they would be able to participate in the payload section, and they would be able to help in the development of this iCubeN. So this was all in the few example missions related to the space of CubeSats. Now, the question is that how Cube satellites are launched once they have been manufactured. So there is some video. Let's proceed to that. So this is basically an international space station, which you are seeing here. And this Cube satellite is being released from that International Space Station. So International Space Station is basically an artificial satellite, a big one, and it is the collaboration of 5 big space agencies: Russia, America, Japan, and Canada. So we can launch the satellites from International Space Station, or we can also launch it with the help of a rocket launcher. So let's proceed to this video. So they launch this from this International Space Station with the help of deployer. So this is an animation video for that. And as you can see that the satellite is tumbling initially. So the attitude determination control system, which we implemented on the onboard, so that would be able to stabilize this satellite. And it usually operates in the thermosphere, meaning in the range of around 500 to 600 kilometers. It orbits the Earth around this much range, 500 to 600 kilometers. So this is another video. In this case also, the rocket is launched from this deployer from International Space Station. So basically there are 2. The first one is of Nepal, Sri Lanka, and Japan. It was a combined Cube satellite made by these countries. And the second one is of Singapore. So let's proceed to the video.
Station Iqbal says ground 2 for Iq for satellite deployment. We'll give you 10-second countdown. 10.
So the first satellite.
8, 7, 6, 5, 4, 3, 2, 1. Deploy. Yo-ho!
So this is how it is deployed from International Space Station. So this one is the BIRDS 3. 3 meaning 3 countries participated in this: Nepal, Sri Lanka, and Japan.
9, 8, 7, 6, 5, 4, 3, 2, 1. Deploy. On time.
And this one is Spooky 1 Cube satellite.
Congratulations.
Okay, so this is how the Cube satellites are launched. It can be launched from the International Space Station, or it could be launched with the help of these launch vehicles. So when in case if they are to be launched from this International Space Station, so when the launch vehicle takes some cargo there, so usually they also take the Cube satellites or whatever the payloads that have to be launched. So one of the option is that, and the other one could be that when launch vehicle goes for some mission to the other planets, so they launch the Cube satellites on their way up at the altitude which is determined like 500 kilometer or 600 kilometer. Usually the Cube satellites, they are launched at this much altitude, around 500 to 700 kilometer. So this was all in the section of how Cube satellites are launched. So that's the end of the talk. I discussed about the 4 sections, the background, history, introduction, and the subsystems, how all these, the Cube satellite is composed of the structure, power system, solar panels. And similarly, I discussed about the applications followed by how Cube satellites are launched. So I hope you find it informative. So if you have any question, you can ask.
Thank you so much, Usman. Audience, if you have any question, you can raise your hand and then I'll give you the mic. All the participants, if you have any question, you can raise your hand and then I'll give you the mic and you can ask the questions related to the CubeSats. Usman, if you can kindly unshare your screen, please.
Okay.
We have to take a group photograph as well. Iman, Kadir, do you have a question? Okay, so I guess we don't have any questions. Participants, if you can please turn on your cameras so we can take a group photograph. Musa, Zohaib, Hur, Fatma. Okay, I think Usman, you have got a question.
Okay, so there is a question in the chat that, sir, are there any other alternative methods of launching? So two of the methods which I told you, that it could be from launch vehicle, or if launch vehicle takes to the International Space Station, it could be launched from there. And one other option is that there was a commercial flight which had a rocket launcher on a launch vehicle on it. So what it does is that usually the commercial flights, they fly at an altitude of around 10 kilometer, or you can say 36,000 feet. So what it does is that it launched the rocket from that 10,000 feet instead of the Earth. And then that rocket goes up to the space at 500 or 600 kilometer, and it launches the Cube satellite from there. So these are the 3 options, the 2 which I discussed in the slides, and the third one which has been with the help of these these spatial flights which had rocket launcher on them. Okay.
Well, there is another question as well. Why was RainCube deorbited? From Hur, Fatma, Siddiq Public School.
Okay. So whenever we develop a satellite, so it has a mission or a life. So when that mission is achieved, or if there is some like its subsystem have stop function, so we have to deorbit that satellite. So that was the reason. And usually the Cube satellites, they have life about 2 years. And especially if there are some more solar cells or more deployable solar cells, then its life could be increased. So that's the reason why RainCube was deorbited, because its life mission was ended. And what is the average life of Cube satellite? So basically it depends on the design of the Cube satellite also, but usually these 2U, 3U Cube satellites with the compact solar panels, they have life around 2 years. But if there is like deployable solar panels, and their life could be increased up to 4 years, 5 years. But in most cases, it is around 2 to 3 years. Okay, so there is a question, can it be upgraded? So basically we can send the commands to the cube satellite from the ground station from the Earth. So yes, it is possible to send the commands to the cube satellite from the ground station.
Okay, thank you so much, Usman, for that wonderful lecture on CubeSat lights. And participants, we have another lecture at 4 p.m. on UNSCG's Achieving Through Space Technology. So I guess we'll see you there as well. Thank you so much, Imran, again.
Okay, thank you. Allah Hafiz.